Schodik from the University of Toronto, who will be co-chairing this session with me, and also Melanie Zeilinger is an organizer from ETH Zurich. Unfortunately, she can't be here with us. So before we start, just a few words about why we have this session. So it's actually the theme of the theme of the session is machine learning and control. And we started this series actually at the last CPC where we had the first invited session on this topic, because we are convinced that machine learning and database learning has great potential for control and dynamic systems, but we really need approaches that combine database learning with rigorous systems and control theory. So we are very happy to have 6 great contributions to this session that are exactly at this intersection of machine learning and control. So I'll hand over to Angela to then introduce the first presentation.
So our first paper is from the University of Berkeley, and it's titled Goal-Driven Dynamics Learning via Bayesian Optimization, and the authors are Soumya Bansal, Roberto Calanto, Tess Yao, Sergey Levin, and Claire Towner. So,
thanks for the introduction, Angela. So today I'm going to talk about goal-driven dynamics learning. So autonomy is increasing at a rapid pace, and with that, our autonomous systems are becoming more and more complex, ranging from the musculoskeletal robots that have been developed to mimic human-like locomotion behavior, to the systems which are human in the loop. And this system by Microsoft, where they are doing indoor farming, but they want to control the light, water, pesticides, and the output is the optimal plant growth. So a natural question to ask is how to control such complex systems. And one approach is to model these systems from the first principles. But often that is too hard or too cumbersome for the complex systems like this. In other cases, we have a good dynamics model for such systems, but that's not enough, and that does not capture all complex behaviors of the system. In such cases, machine learning provides a very good alternative because it has the capability to control the system directly from the data collected on these systems. When it comes to machine learning, the approaches to control the systems are divided into 2 broad categories: model-based learning and model-free learning. Model-based learning aims to learn a system dynamics model and use it for control purposes, except that this model is now learned from the data. In particular, they maintain, or at any given time during the learning process, they maintain a system model F with state X and control U. That model is then used to design the controller by using them in the combination with the optimal control schemes, which is then executed on the real system, which is this robot here. And then based on that, you collect more data and then you refine the model, and then you repeat this entire process. So just a note here, for the consistency's sake, throughout this presentation, I will use a blue loop to denote a closed loop control applied on the real system. Similarly, a purple loop to denote a real experiment, meaning something that is executed on the real unknown system here. And then a red loop to denote learning. Okay, so going back to model-based versus model-free. Model-free learning do not maintain a dynamics model and instead try to learn controller to control the system directly. In particular, they try to maintain a controller pi, which takes in the state and gives me the control that I should apply, which is then applied on the real system and again refined in a similar fashion based on the data. And each of these approaches have their pros and cons. Here I would argue that I would go with model-based learning because they are data efficient. And by data efficient here, I mean that within a few experiments, they can learn a very good controller for the system. And that's a very key property that we want in our robotic system, because each iteration here is a real experiment of the system, and collecting data or experimenting on the real system is often expensive. So now let's take a look at the problem that the model-based learning is trying to solve, or what that problem looks like mathematically. So again, we have an unknown system S, which will be this robot throughout my presentation. And we have a cost function, which I'm using as a proxy for the task that I want to get out of, or that I want to solve, or that I want this robot to perform. So in particular, I have a cost function J, which is a function of my state and input trajectories. And I want to learn a system model F, which is again a forward dynamics model here. So suppose you give me any model F for the system, then given this cost function and this system model, I can design an optimal controller for the system. And again, this is not an easy problem to solve, but here I'm assuming that we can use some of the optimal control schemes to do that. And then when we apply this controller on the real system, we will get some cost value. And that is what I'm denoting here by JSUF, which means that the controller UF, when applied on the system S, give me this cost value. In particular, whenever we do any experiment on the real system, we get two sorts of data. One is the trajectory data, which is the state and input trajectory that the robot followed. The other data is the cost value. And the learning problem here is to find the model F, which minimizes this cost value here. Again, this is the cost on the real system, not on the system model. Graphically, if I were to plot all classes of models along the x-axis, so all possible models that exist along the x-axis, and their corresponding performance on the real system on the y-axis, then we want to find the model which gives me the minimum cost value. And this learning problem is generally done in an indirect way most of the times. In particular, a good prediction model is used as a proxy for a model which can give me best control performance. Generally, what we do is we take this trajectory data and fit a dynamics model which minimizes the prediction error, and then we use that model to design the controller for the actual system. But that approach has several limitations. To begin with, that approach suffers from something called model bias, which is that it doesn't take into account at all the performance of the model, and as a result, there is no connection between the actual task that I'm trying to solve and what I'm learning. And that could result in a suboptimal performance. Here we propose a new learning scheme directly based on the performance observed on the system model, because that's the number that I care about here. And we will show that it has two advantages. One, it gives me better control performance. Two, it allows me to control the system with a much coarser, a much inaccurate prediction model. Okay, so let's look at the framework now, which we call ADOBO, which stands for Dynamics Optimization via Bayesian Optimization, because of the tools that I'm going to use in this project. So we learn here the simplest system model, which is the linear time invariant model. Again, this is just a system model. My actual system can totally be nonlinear. I'm just learning a linear model for that system. So going back to the graph that I drew earlier, now we want to find the best linearization to give me the minimum cost on the actual system. Now again, once I have the system model, I can design a controller using optimal control scheme. And then I apply it on the real system and I get some performance value. That performance value then goes in the Bayesian optimization, which I would elaborate on in a second, and that further refines the model. Now what does Bayesian optimization do? At a very high level, Bayesian optimization is a zeroth order optimizer, which only takes in which can optimize a function just based on querying that function. So it doesn't require any gradient information about that function and so on. In particular, here we are interested in optimizing this function to find this A star and B star. And Bayesian optimization exactly does that by taking into account all the past experiments or past queries that you did and coming up with the next query in a smart fashion. Okay, so now let's take a look at an example. So the first example is very canonical control example. This is Dubin's car here. The Dubin's car is a three-state system, or we generally model as a three-state system with x and y position and the heading on the xy plane. There are two controls, the speed of the car and the turn rate of the car. Here, my objective is to minimize this cost function here, which is a quadratic cost function to regulate the system state to 0, 0. And these are the dynamics of the Dubin's car. Here, we know the state of the system, control of the system, as well as the cost function that we want to minimize, but we don't know the dynamics. We don't know how this state evolves. And our goal will be to learn this linear model, such as to optimize this cost function on this real system right here. Okay. And we will do that using the framework that I just described. So here are the results. So let me interpret the results for you first. So for the comparison purposes, we actually use the dynamics model to design the optimal controller, which in this case was done using MPC. And here I'm comparing the performance of the controller as the learning progresses along the x-axis. So each iteration here is one learning iteration. On the y-axis, I'm comparing the performance of the controller obtained through this model compared to the optimal controller, designed using the full nonlinear dynamics. And within 50 iterations or so, I'm able to achieve within the 5% of the optimal control performance. And looking furthermore on the trajectories that are obtained using this system, using this linear system here versus the actual system, you can see the state trajectories align pretty well. And these are the x, y, and the control trajectories here. So I think most of us will be thinking that, okay, so that makes sense. Maybe for a lot of nonlinear systems, it's enough to find a good linearization of the system, and that should be enough to control the system. And that's what I thought too. So what we did is we did a very small experiment, on the linear system in particular, and see if indeed we are finding the linearization of the system. So again, this is a linear system, unknown for our purposes. It's a one-dimensional linear system here, and the cost function is quadratic as before. But instead of using the optimal control directly, I decided to use my framework, Adobo here, to design a controller. So essentially, we will learn a linear dynamics now with parameters θ1 and θ2 here instead of a and b, because these are one-dimensional parameters in this case. So going back to the picture, we want to find the θ1 star and θ2 star, which minimizes this cost function on the actual system, which in this case is given by this linear system, which is unknown to us. So here, what I'm doing is I'm plotting the same cost map in this heat map over here. Remember, these are the two-dimensional. This is two-dimensional parameters. So the first parameter is along the x-axis, the second parameter is along the y-axis, and this is the performance obtained by that particular dynamics model on the real system. And in this case, obviously, the optimal linearization is 1 and 1, because the actual system is indeed linear, which is this red star over here. That should give me the best control performance across all model class. But what learning does is actually it finds this dynamics model right here. And I was very surprised because I thought it should actually learn a good linearization of the system. But when I looked at this graph, I realized that there is this lower dimensional structure that exists in this space which allows it to learn very efficiently, number one. Number two, it can control the system with a very coarse model, because any model along this line will give me the same control performance. So it answers one of the very key questions in control, which is how good of a model I need to learn to control a system. And maybe the answer is not so accurate. I mean, maybe I can just design a good controller with a very coarse model. We further tested our algorithm on real quadrotors using the quadrotor that we are flying here is Crazy Fly 2.0. The task here is to regulate the quadrotor from an initial position to a desired xy position. And again, the dynamics are unknown for the xy evolution. For the comparison purposes, we compared our design controller against the full 12-dimensional nonlinear model of the quadrotor. And this is the curve we got. So when we start with a very random initial model, so we are actually performing worse than the nominal controller. So by the way, this is the percentage error with respect to the nominal model as the learning progresses. So we start below the nominal controller, which is not surprising here. But as the learning progresses, within like 20 or within 7 or 8 iterations, we outperform the nominal controller, and finally the performance saturates at 12% up of the nominal controller. So we do perform 12% better than the best 12-dimensional model that can be used to design this controller. And this is because this is learned, the controller here is learned using the actual data on the system. So it can compensate for the errors in my model. So a natural comparison would be against indirect adaptive control or traditional system identification approaches, where you first learn a prediction model and then use it for the control purposes. So that's what we do here. We again learn a linear time invariant model for the dynamics and see how that performs, except that now this linear time invariant model is learned using trajectory data. So these are the numbers that we get as the learning progresses. So again, this is the learning iteration, this is the performance of the proposed algorithm, and this is the learning by least squares or indirect adaptive control, where in each iteration we collect the trajectory data, we learn a linear model, and then design the controller using that. And these results are for the Dugan scar. And we see that the indirect adaptive control is not able to compensate for the errors in the similar way, especially when you have a simpler class of dynamics. I'm sure that if I use more complicated class of dynamics on Dugan scar, probably the input trajectory data based learning would actually eventually work out. But the main message here is that when we use alternative structures for learning, then we can get away with much simpler class of models. Okay, so I would like to summarize. We saw that as for our autonomous system, we need data-driven control because they are becoming more and more complex. And the broad categories for these learning approaches is model-based and model-free approaches. We saw how model-based approaches are very data efficient, but suffer from model bias. We propose a new scheme to do this learning, but in a goal-driven fashion, where instead of trajectory data, we learn directly based on the observed performance. And then the advantages we saw is that it leads to a better control performance because it directly does learning based on the performance. And two, we are able to control the system now with a much coarse dynamics model. So there are a lot of future directions here that I'm interested in. The first one, and the natural one, is when does such a low-dimensional structure exist? Because the whole premise is that because of this low-dimensional structure, we can do learning in a more efficient fashion. The second, and probably a much broader question, is what is the trade-off when we learn in the dynamic space, like I'm doing here, versus directly designing the controller, or direct adaptive control, for example. The other thing is, I haven't taken into account the safety at all. While learning, my quad order crashed, and what I want to do is I don't want that to happen, right? While I'm learning. So how to combine them with the safety approaches to make sure that my learning is safe? Then how we can generalize across tasks, because this was a very task-specific model, but often with the models we want to do multiple tasks. And so how we can learn a model which is general across tasks. And finally, how we can scale this approach to higher dimensional complex systems. So with that, I would like to thank my collaborators, and I'm happy to take any questions.
Are there any questions? Yeah, in the back and then.
So how sensitive is the learning to initialization?
It's not very sensitive. As you could see, there were standard deviations along the plots. So here, for example, these standard deviation, sorry, I should have explained it better, but this is the mean curve and this is the standard deviation as you do different initializations. So certainly initially there is a huge standard deviation, but it converges pretty fast to a very narrow tube.
And there was one question.
Yes, so when you're trying to learn the dynamics, there are several iterations, and for each iteration, do you use the same initial condition and the cost function? Or do you use different initial condition and the cost functions?
Good question. So I think in this particular simulation, that is the case, that I'm using the same initial condition and same cost function. But that we faced this challenge when we were doing quad order experiment, because it was very hard to initialize the quad order at the exact same position. So here there was some noise in the initial state as well.
But the cost function is the same.
The cost function is same. Okay. So this is a very task-specific
so trying to stabilize the quad order through a stabilization, right?
That is correct.
Okay, thank you.
One in the back.
I'm wondering why do you restrict the model, the main model, to be linear with A and B instead of general neural network?
Because we don't want to, okay, so there are several reasons. Number one is, for the system that I'm working with here, I believe that linear model should be enough to control the system. That's number one.
Dubin's car is very long.
Sorry?
But Dubin's car is very long.
Yes, but just that a linear model should be enough to control it. Certainly there could be a better optimal control that you can design using a non-linear model. The second thing is, I should be able to solve the this optimal control problem here very efficiently. And so if it's a non-linear system, then I'm essentially going in a loop where now I have a better model, but I can't solve the optimal control problem efficiently. So linear model allows me that flexibility.
And you have one last
Yeah.
question.
How do you determine the system order of your linearized model?
So, good question. So here I assume that I know the state of the system and what my controls are. So the order of the system is simply nx squared, where nx being the number of state, plus nx times nu. So A and B matrices essentially for my state space and control space.
Yeah, but how do we determine the order of the state, dimension of the state? It's very difficult.
Agreed. And here I'm I'm assuming that I know what these states are, that I enough to control. Thank you.
Okay, let's thank the speaker one more time.